800 light-years away, there's an unseen antimatter factory churning out high-energy positrons, tiny particles of antimatter that are streaming through the cosmos and colliding with our planet. For much of history, we didn't know this strange source existed. Most of the positrons bombarding us went completely undetected, instead getting absorbed in our planet's atmosphere. It wasn't until we started looking from beyond the bounds of our planet that we noticed them. In 2011, NASA's Alpha Magnetic Spectrometer, a state-of-the-art particle detector some 200 miles up aboard the International Space Station, was switched on. What did it find? You guessed it, positrons. The presence of these subatomic particles was to be expected, but not in the numbers they were finding. Such was the sheer volume of positrons being detected, that the usual sources like natural radioactive decay and cosmic rays no longer offered a sufficient explanation. So, where were they coming from? We've only recently been able to trace the culprit of this cosmic antimatter shower, and it all comes down to another high-energy discovery. A strange gamma-ray haze named Geminga, first identified in the 1970s. What is this mysterious source of gamma radiation, and what does it have to do with the unusual abundance of high-energy positrons hitting our planet? I'm Alex McColgan, and you're watching Astrum. Join me today as we tune into the enigmatic frequency of Geminga, whose gamma radiation has lit up the world of astrophysics for decades. Up in our night sky, nestled in the Gemini constellation in the northern celestial hemisphere, there is something peculiar going on. In 1972, NASA's Small Astronomy Satellite 2, or SAS-2, identified an unknown source of gamma radiation. But with the technology available at the time, the best it could do was trace its origin to this wider region of our Milky Way. So the radiation's ultimate source remained hidden among the stars for decades. Nevertheless, it was given a name, Geminga, as coined in 1976 by Italian physicist Giovanni Bignami, who would dedicate his career to studying it. It's a play on words, a combination of Gemini, the region where it's located, and gamma, the type of radiation it emits. Geminga is also a pun in Bignami's Milanese dialect, meaning "it is not there," a fitting name for a gamma-ray haze with an unknown origin. It wasn't until 1983 when Bignami and his team finally had their big break. They managed to identify a weak X-ray signal from Geminga using the Einstein X-ray satellite. This meant, although its exact position remained unknown, they could narrow down their search area and were getting closer to uncovering Geminga's hiding place. But it didn't answer the big question, what is it? As astronomers could still only offer vague guesses about the true nature of the source. Then that was until 1991 when they had another lucky break. 2 separate missions identified radiation coming from Geminga, and they weren't constant signals but pulses. The first of these discoveries was made with a German-built X-ray telescope known as ROSAT, short for Röntgensatellit, named after the German word for X-rays. ROSAT was the first to identify pulses in the X-ray signal coming from Geminga, and soon after they were also confirmed in the gamma wavelengths by the energetic Gamma Ray Experiment Telescope, or EGRET, a telescope aboard NASA's Compton Gamma Ray Observatory satellite. Not only did these complementary observations demonstrate that the X-rays and the gamma rays were both coming from Geminga, but for the first time they revealed what Geminga was. With a period of 0.237 seconds, flashing as it spins around its axis a little more than 4 Hz or 4 times per second, Geminga behaved like a pulsar. A pulsar is a type of neutron star that spins rapidly, emitting beams of radiation that sweep across space like a cosmic lighthouse. From across the galaxy, most pulsars appear to flash in radio waves, anywhere from a few times a minute to as fast as 700 times per second. And at this point in the early 90s, they were incredibly rare. You see, before ROSAT and EGRET, only 2 other high-energy gamma-ray pulsars had ever been identified, the Crab and Vela pulsars. And Crab and Vela were different to Geminga in a couple of key ways. First, in addition to gamma rays, both of these pulsars also produced radio waves and were therefore visible using radio telescopes. So if Geminga was a pulsar, then it would be the first discovery of one that was apparently radio silent, only emitting enough radiation to be seen in the gamma and X-ray wavelengths. And second, Crab and Vela are surrounded by their respective nebulae remnants from when they were created from supernova explosions. But Geminga's nebula was conspicuous by its absence. So why is Geminga, this powerful source of gamma rays, so good at hiding from our radio telescopes? Where is its nebula? Or could it be a different type of object altogether? Well, the answer to the first question is in part because we hadn't been listening properly due to the limitations of the available technology and due to our understanding of the radio emissions of such stellar remnants. You see, while radio pulsars can emit radio waves across a wide bandwidth from as low as 17 megahertz to above 87 gigahertz, around half of the radio spectrum, not all of these frequencies travel well through space. Even though we've known since the 1970s that radio pulsars often peak between 100 to 200 megahertz, where they are intrinsically brightest, things like the interstellar medium, background sky temperature, and effects from the ionosphere mean that lower frequencies are dampened as they make their way across space, resulting in very weak signals that are more difficult to detect. Because those radio signals are so weak, most radio telescopes hadn't been looking for them, instead confining themselves to searching for signals between 430 and 1600 megahertz. This would have been fine had Geminga behaved as expected for one of its kind. Since it did not, it took until 1997 for scientists to realize what was happening. 3 independent observations from the Pushchino Radio Astronomy Observatory were able to identify extremely weak pulses from Geminga using a sensitive transit antenna. The faint radio pulses came in around 100 megahertz, which explains why previous radio searches for Geminga had come up silent. Turns out Geminga wasn't truly hiding and had been sending us signals. We just weren't listening correctly. That same year, a team led by the late astronomer Janusz Gill theorized that another reason Geminga had appeared to be radio silent may be its magnetic field. Models showed that the radio waves may be absorbed or refracted within the pulsar's magnetosphere, leaving only weak pulses around 100 megahertz to be detectable. This would effectively leave it quiet at the higher radio bands that most telescopes used. Confirming Geminga was a pulsar, and specifically a gamma-ray pulsar, was a big deal. In fact, 99% of its output is in the gamma range, making it one of the brightest gamma-ray sources in our entire galaxy. It is, as it turns out, all that's left after a star, several times more massive than our Sun, exploded about 350,000 years ago. But its relative radio silence and its apparent lack of a nebula weren't the only unusual things about this pulsar. When Italian astrophysicists, including Bignami, Geminga's name-giver, compared a series of observations from the European Southern Observatory's ESO 3.6-meter telescope and New Technology telescope with observations from the Canada-France-Hawaii telescope, they found that Geminga was moving. Not only that, it was traveling at an unusually high speed of around 0.2 arcseconds per year. As a reminder, an arcsecond is a very small unit of angular measurement used when we need more precise measurements than a degree would allow. Within each arc degree there are 60 arc minutes, and within each arc minute are 60 arcseconds. These arcseconds are a common unit used in astronomy to talk about the movement of objects across the sky. From our perspective on Earth, if you were to draw a circle around the orbit of the Moon, around the Earth, there would be 360 degrees around that circular path. So at any given time of day or night, assuming nothing is blocking your view of the horizon, you can see about 180 degrees of the sky, and from the horizon to the zenith, the top of the sky is 90 degrees. If you hold out your little finger at arm's length and close one eye, the tip of your little finger covers about 1 degree of the sky, roughly. Next time you're outside on a clear night, try this and see if your little finger can cover the moon. It should, because the moon takes up only about half of a degree, or about 31 arc minutes in the night sky. Geminga, traveling 0.2 arcseconds across our sky each year, may not sound like a lot, but from our perspective on Earth, the typical star only moves a few thousandths of an arcsecond per year. Yet despite being 800 light-years from us, Geminga will travel 30 arc minutes, the equivalent to the apparent diameter of the moon, across our sky in just over 10,000 years. In other words, this stellar corpse is racing through the galaxy at nearly 210 kilometers per second. Heading toward the border between the constellations Gemini and Lynx, and at its current rate of motion, Geminga will remain in Gemini for another 500,000 years, but it may need a new name after that. However, this mysterious pulsar gets stranger still. It's its vast speed that helps produce another feature that scientists were about to discover. As it hurtles through space, Geminga leaves behind two ghostly X-ray tails that streak 3 trillion kilometers across the sky. As I discussed earlier, despite the fact that this fast-moving pulsar is nearly radio silent, it certainly isn't quiet in the gamma-ray and X-ray wavelength. In 1999, ESA's X-ray multi-mirror mission, or XMM Newton, was launched to peer deeper into this X-ray universe. And 4 years later, a team led by Patrizia Caraveo uncovered these comet-like X-ray trails. Their shape and brightness are partly explained by the shockwave created by Geminga's motion through space and its rotation as a pulsar. But they are also revealing of another attribute, Geminga's colossal mass. Measuring only about 20 to 30 kilometers across, Geminga is extremely dense, containing about as much mass as 1.5 of our suns. To put that in perspective, if you had a teaspoon of neutron star material, it would weigh about 4 billion tons, as much as 10,000 Empire State Buildings. As this dense, high-mass object races forward through the low-density interstellar medium, just 0.06 to 0.15 atoms per cubic centimeter, it compresses the interstellar medium and its own embedded magnetic field by a factor of 4. Meanwhile, the incessant spinning of the neutron star creates an environment where electrons and their antimatter counterparts, called positrons, can be accelerated to extreme energies, powerful enough to emit high-energy gamma rays. While most of these electrons are seen in the gamma radiation that escapes from the pulsar, some get trapped and spiral within this enhanced magnetic field. In these images from a computer model, the tails can be seen streaking along the edges of Geminga's three-dimensional shockwave, like the wake created by a boat going through water. Only this boat is more massive than our Sun, and the wake is made up of extremely high-energy X-rays. But the final piece of the Geminga puzzle wasn't discovered until 2005, its nebula. Taking the form of a shell of neutral hydrogen gas with a radius of 0.4 parsecs wide, it turned out to be what we call a pulsar wind nebula. This type of nebula is created from the wind of plasma that emanates from a pulsar's magnetic poles. The plasma, made of charged particles that can be accelerated to near light speed, surrounds the pulsar, creating a nebula of high-energy particles that give off strong X-ray emissions. With the confirmation that Geminga did have a nebula, its identity as a pulsar could finally be confirmed. But Chandra went even further. In addition to imaging Geminga, Chandra also looked at a second pulsar called B0355+54, and by comparing the two, astronomers uncovered another possible explanation for the absence of radio pulses from Geminga. On the surface, these pulsars seem quite similar. They are both about 500,000 years old, and they spin about 4 or 5 times per second. However, as you know, Geminga is seen primarily in gamma-ray pulses with no bright radio emissions. By contrast, the other pulsar, which I'll refer to as Pulsar B, is not seen in gamma rays and instead is one of the brightest known radio pulsars. How could these two pulsars be so similar, yet so vastly different in how we see them? The answer may be as simple as how each of these pulsars are oriented relative to our observation from Earth. Astronomers believe that these images of Geminga and Pulsar B have revealed their spin axes and uncovered a reason for why radio and gamma-ray pulses may be present or absent on different pulsars. Like our own magnetic field around Earth, both of these pulsars have magnetic poles close to their spin poles. These poles are where the beams of pulsing radio emissions come from. You could try to model this if you skewer a little foam ball right down the middle. The foam ball is a pulsar, and the radio beams coming from the poles are represented by the wooden skewer coming out both ends. If you spin the ball around the skewer like a spin axis, you create an equator around the middle. To illustrate the gamma-ray source along the spin equator, called the torus, you could cut a hole in a paper plate and squeeze it over the foam ball. Now you've got yourself a disk of gamma rays beaming out from the equator in every direction. With Geminga, the edge of the paper plate is pointing towards us, meaning the gamma rays are heading to Earth. But for Pulsar B, its relative position to us is at a different angle, as if looking at the flat surface of the plate. The gamma rays are moving perpendicular to our line of sight, therefore missing Earth. Let's look again at the two Chandra images of Geminga on the left and Pulsar B on the right, along with artist illustrations of what astronomers believe the pulsar wind nebulas look like for each of these. In the image of Pulsar B, the long trailing blue tails represent the radio jets emanating from its poles and the skewer coming out of both ends. Only instead of being straight like a wooden skewer, Pulsar B is moving so fast through space that these jets appear bent backward, trailing behind as the pulsar moves through space. Now look at the image of Geminga here. The long twin tails on either side of the image are the radio jets trailing behind as it, too, rushes through space. But this time, instead of pointing almost directly toward and away from our vantage point on Earth, these jets appear to be pointing off to the sides, not aimed at Earth. So when astronomers look at Geminga, they see powerful gamma-ray emissions from the spin equator, but the radio jets point to the sides and remain unseen. And when they look at Pulsar B, the opposite happens. The radio jets are pointed almost straight toward our planet, while the gamma-ray source at the equator is missing Earth. Sometimes the most simple explanation is the correct one. And that finally brings us back to the decades-long mystery of an unusual abundance of antimatter bombarding our planet. For more than a decade, a particle detector called the Alpha Magnetic Spectrometer, or AMS-02, has been attached to the International Space Station, collecting information on antimatter, dark matter, and cosmic ray sources. As a reminder, cosmic rays are energetic particles, fragments of atoms that travel through space at nearly the speed of light. These can be made by the sun, by supernova explosions, or other cosmic means. And in 2013, the first results of the AMS-02 experiment were announced. The detector had recorded more than 400,000 positrons, the largest sample of cosmic ray positron data ever collected, and increasing the world's total cosmic ray positron data by 100-fold. For years, many astronomers and physicists hoped that this excess antimatter may be the byproduct of dark matter annihilation, offering possible clues about this mysterious substance. After all, dark matter could make up around 27% of the cosmos, and yet we still don't know what it is. Like regular matter, dark matter holds mass and takes up space, but it doesn't seem to absorb, reflect, or interact with light, at least not in a way we can detect. Some theorize that dark matter may be made of yet unidentified types of particles. Whatever it is, scientists had high hopes that the overabundance of antimatter being detected aboard the ISS may hold clues about dark matter's true nature. Unfortunately, they've been left disappointed. The more scientists dig into the data, the clearer it's becoming. The most likely source of these positrons may actually be pulsars. Astrophysicists had long suspected this, but until 2017 there simply wasn't proof. It was the high-altitude Walter-Cherenkov Gamma Ray Observatory, HAWK, that finally added evidence to this hypothesis. A small halo of gamma radiation was identified surrounding Geminga with trillions of times more energy than is visible to our eyes, from 5 to 40 trillion electron volts, the sort of radiation usually produced by positrons. This was the first real observational evidence pointing to a pulsar as a potential source. Pulsars naturally surround themselves with a haze of both electrons and their positron counterparts, as a result of the star's intense magnetic field. This intense magnetic field pulls particles from the pulsar's surface and accelerates them to near the speed of light. Scientists think that these accelerated positrons and electrons are then colliding with starlight, boosting the light to higher energies, which then radiates as the gamma-ray halo observed. But based on the size of the halo the HAWK team saw, Geminga's positrons would rarely have the energy required to reach our planet, and so they believed that the excess positrons must have a more exotic source. That was until stunning new information was uncovered a few years later, thanks to a team led by astrophysicist Mattia Di Mauro. Using a decade of gamma-ray data about Geminga, acquired from Fermi's Large Area Telescope, which is able to observe lower energy light than the HAWK Gamma Ray Observatory, DeMauro's team was able to subtract out all other gamma-ray sources to reveal a spectacular glow coming from Geminga, much bigger than what scientists had ever seen before. This vast oblong halo of glowing gamma rays at an energy of 10 billion electron volts spanned 20 degrees of the sky, similar to the area the Big Dipper constellation occupies. And that's not all. The glow of gamma radiation is even bigger at lower energies. If we could see it with the naked eye, Geminga's gamma glow would dominate our sky, covering an area 40 times bigger than the full moon. With this new information, astrophysicists found that the size of Geminga's halo meant this one pulsar alone could be responsible for as much as 20% of the excess positrons detected near Earth. From there, it's no stretch to imagine that other pulsars are the most likely culprit for the remaining antimatter abundance we found. This explanation may not have solved the mystery of dark matter, but it is certainly a magnificent revelation. It was Jocelyn Bell Burnell who discovered the first pulsar in 1967, back when people thought that those regular signals could be the work of extraterrestrial life. In the nearly 60 years that have passed since, we have found thousands of pulsars, and our understanding of these neutron stars has grown with everyone. And since Geminga was identified as only the third known gamma-ray pulsar in 1991, we've now spotted over 300, thanks to NASA's Fermi mission. But given Geminga's track record of defying expectations and furthering science, I like to think that this particular pulsar has more secrets still to reveal. Solving the mystery of pulsars like Geminga can't be done without the right knowledge. Mathematics, the physics of light, engineering know-how, these types of skills are vital to any would-be solver of the unknown. But sometimes getting proficient in STEM subjects like these can feel a little daunting, particularly if you're feeling a bit rusty. But don't worry, you just need the right teacher, like the sponsor of today's video, Brilliant. Brilliant is an excellent online learning platform with thousands of visual and interactive lessons in math, science, programming, data analysis, and AI. I really enjoy its engaging UI and accessible structure, like this one on finding unknowns using equations. Brilliant keeps you thinking with interactive questions and then helps you really understand the answers. It's proven to be 6 times more effective at helping you master something than just watching lecture videos, with courses written by award-winning teachers, researchers, and professionals from Stanford, MIT, and other institutions. To learn for free on Brilliant, go to brilliant.org/astrum, scan the QR code on screen, or click on the link in the description. Brilliant's also given our viewers 20% off an annual premium subscription, which gives you unlimited daily access to all it has to offer.